Now we are live, browser. You may begin the session.
Okay, so I will also begin with some problems, and we will see what concepts can we learn through these problems. So you all can read the problem that is on my screen.
Yeah, I am able to read. The students can respond.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. Okay. So maybe now you can try for 1 minute and then tell me how you want to proceed, so that I will know what you are thinking, and that might help me to do the problem. So Deepika, can you read the problem and tell me what you understand?
Yes, sir. Consider a quantum mechanical system with three linear operators A, B, and C, which are related by AB minus C is equal to unit vector. If A vector is equal to d by dx and B vector is equal to x, what is C? So here given the relation between A, B, C operators, sir, then what is the C value?
So
I think it's a direct apply method, sir. I don't know.
Okay, so correct. So that is fine. But what do you think is the way to do it? How do you find C?
Sir, I have a two ways, sir. One is direct method, sir. That means I put just the A cap value and B cap value in direct in the equation, sir. That means A cap, B cap minus C cap is equal to 1. So that is the way.
So C,
I
so
get
according
option.
to you, C will be equal to A, B minus 1. Is that correct?
But at that time we will get only answer is 0, sir. So maybe a commutator it will be using, sir.
No, there is no commutator. No here.
That means. Sir,
So you are
know,
no, that is fine. But you are thinking that that directly substituting. What is the second way? You said you have two ways.
Yes, sir. First, no,
One
sir.
way
That
is
is
direct substitution.
Yes, sir. Another one, I'm using the commutator model, sir. But here, just giving the operators, sir. So I think
somehow
we cannot.
Direct substitution.
Yes,
direct substitution. Even though you are saying direct substitution, but you seem to be not very comfortable doing that, right? You have a doubt that it may be wrong. Yes or no?
Yes, sir. Because the answer is my answer C, we will get only 0, sir. I think maybe it is wrong.
Okay. Okay. So any Pandya Rajan, do you have some idea?
No idea, sir. Sorry.
What do you do? Such a problem is given, and only if you solve this problem you will pass the course, otherwise you will fail. Then what will you do? You will try something, right? You don't want to fail, right? So with the available knowledge, what will you try?
Apply the AB value. So dx by dx. So then 1 minus c vector is equal to 1 vector. Something but I wrong.
So like what Deepika is saying, you will get 0 in that case, right?
Yes, sir.
Excuse me, sir.
Yeah. Yes,
Sir,
Deepika.
maybe we will use this method, sir. That means linear operator. That means wave function. We put the wave function, sir.
Where do you want to put the wave function?
Sir, the operator section.
Where do you want to put the wave function? Correct. You are thinking in the right direction. A little bit amplify what you are saying. Somehow we have to bring wave function into the picture. That much you understood, right?
Yes, sir. Because here given 3 linear operators, sir.
Okay.
So sorry, sir.
Okay. Devishmita, do you have some suggestion?
Yes, so we will operate this relation like AB cap minus C equals 1 cap to a wave function. So it will be like A cap B cap operated over psi minus C cap operated over psi will be equals to 1 cap operated over psi. So A cap B cap will be d by dx of x psi. Then we'll have to take its derivative with chain rule like that.
Product rule.
So by that's like yeah.
Okay,
then
why should
it will
we?
Be like.
Okay, you are right, but why should we do it like that? Why should we operate it on a wave function?
Sir, I believe like operators cannot be treated independently. They are operators, so they need something to act upon. Then only will find their properties.
Okay, very good. Debanjan, you want to say final word?
So I have found the minus x d by dx as the answer. So we have to use the test function, because if we don't use the test function, then we will drop the term that is arising out of the chain rule or the product rule. And because operators are not same as not equivalent to the real numbers, or that we can commute, or like it is a different properties. Linear operators have different properties. So we have to use the test function, otherwise we will drop a few terms. The one term we are dropping. This minus d by dx. So if we drop that term, then the answer will be 0, which is wrong.
Okay.
That's my conclusion.
Okay. So I think from all the discussion that I have heard from you, so the concept here is that an operator is defined. An operator is defined only through its action on the states. Okay. So if I have to know what is A, I can only ask what it does to an arbitrary function, arbitrary state. That only defines the operator. So because of that, whenever you are talking about operator equations, they make sense only when you, so for example, if you want to interpret this AB minus C is equal to 1. This is identity operator. Some of you are saying unit vector, but this is an identity operator. This equation implies when AB minus C, this one acting on any arbitrary function psi of x, we will get identity operating on psi of x. What is identity operating on psi of x? Psi of x itself. Identity does not change the state. So without this function, this operator equation does not make sense. So this is something which you have to keep in mind always. Okay. Now you can ask a question. Now use the data given. Your A is given as d by dx, B is given as x. Okay. So we have, yeah. Yeah, what is the question? Okay. So now second thing, so this is one important information or which is one important learning that you have to keep in mind. Second is that when you say that when A is operating on psi of x, what does that mean? That means it is d psi by x. And when x is operating on psi of x, sorry, that is B. Okay, so that is B is operating on psi of x is simply x into psi of x. Okay, so this is our convention, correspondence. So now you interpret A, B operating on psi of x minus C operating on psi of x should be equal to psi of x. That is the given equation. That is equal to d by dx of x into psi of x minus C acting on psi of x is equal to psi of x. So now you can take it this one to the right hand side and bring that here. Then you have C acting on psi of x is equal to, this one is, this is, you use product rule here. So then you get psi of x plus x into d psi by dx minus psi of x. Correct? So this psi of x and this psi of x will cancel. So you get C is equal to x d by dx. Because psi of x is there on either side, so you get C is equal to x d by dx. Okay. Is this clear or any question? Deepika, is it clear?
Thank you so much, sir. Yes, sir.
Pandyarajan?
No, okay, sir. Thanks.
Okay. Now, we have this interesting relation in quantum mechanics, namely, the commutator of x operator and p operator is equal to IH cross. How do we understand this relation? This relation is IH cross into identity up. IH cross is a constant, right? H cross is a constant, I is square root of -1. And left hand side you have operators, right hand side also you should have operators. So when there is nothing like that, you have to understand this is an identity up. Correct? So even if you want to prove this, okay, suppose if I say that x acting on some psi of x is equal to x into psi of x, and p acting on some psi of x is equal to h bar by I into d psi by dx. Okay. Now, using this definition of these operators, if you want to show this, how can you show this? How can you show this? That means what you have is x cap p cap minus p cap x cap. This is equal to how much? If you ask that question, you can only show this when you consider an arbitrary function psi of x and operate it up. Correct? So this will be given by x d by dx into psi of x. Okay, so let me put that h bar by I outside, minus d by dx x psi. So now this is a product form. So you get x d psi by dx, that will cancel with this, and minus psi you will get. So that will give you h bar by I into psi with a minus sign. Now you take this I to the numerator, you will get IH cross into psi. And that is what gives you that xp minus px on psi of x is simply IH cross psi. That means this is like identity operating on psi. That is how this Heisenberg's commutation relation is understood. Okay. So is this clear? Okay, if it is clear, now I want you to read the next problem. Okay, you have been doing some problems with the matrices, I think last class, maybe before. So we have a quantum mechanical system in some basis is represented by a vector like this. That means we have a three-dimensional system or a three-level system, if you want to call it. So there is a this is the state. Okay, so this is the state. The operator A corresponding to a dynamical observable is given in the same basis by this matrix. Okay. Now, if a measurement of A is made on a system in a given state, this is the given state. What is the probability that the result is +1? What is the probability that the result is +1? So how do we approach this problem? So think about it for a minute.
Sir, can I make a comment? Like, I'm not sure.
Ah.
We have to find the expectation value first. Like, then the expectation value formula is summation probability times the eigenvalues. So there we can find the probability that the eigenvalue is +1. For this, is that the way you can find this?
Yeah, you have to find what is the probability that the what is the probability. See, when you say the result is +1, what can you conclude? If you measure A, the result is +1. From that, what can you conclude?
Like, it has 3 levels, so like energy +1, 0, and -1.
We don't know that. What are the levels? What are the energies of that? We don't know.
So probability is certain actually. Probability is certain. Probability is +1 is certain.
No. It's not probability +1. It is probability of the result is +1.
Okay. Result is +1. Okay. We have to
Yes.
find the eigenvalues. And one of the eigenvalues will be +1.
Yeah. That is what I wanted.
Okay.
So if the result is +1, means we have the information that +1 is one of the eigenvalues. Correct?
Yes, sir.
Without finding, you don't even have to find, because they said result is +1, because the result of any observable has to be one of its eigenvalues. Okay, that is the structure of quantum mechanics. That is the postulate of quantum mechanics. So if they say result is +1, then we know that +1 is an eigenvalue of A. We don't have to find out to say that. Is that clear?
Yes.
Yeah. For others, is this clear? Deepika?
Sir, I need some time, sir.
Okay. What are you thinking?
Excuse me, sir.
Tell me.
Sir, first of all, I have one doubt, sir. So the A is a given operator here, sir?
Yes.
Yes. Sir, the operator is acting on the wave function, sir. We will get a eigen value, sir.
Are you getting like that? When you operate A on the psi, is this psi an eigenstate of A? Devismita?
Yes, sir.
So what are you thinking?
I haven't dealt with matrix wave function for operators, so I want, like, I'm thinking like how to relate it with the conventional way.
So what is your conventional understanding with respect to operators and wave functions, etc.?
So at first we were operating that operator on the wave function which was given. then its eigenvalue will come out like that.
It will come out only if it is an eigenstate. No? See, when you operate A on psi, it may not be even psi, no? For example, in this particular case, you operate A on this psi, you will not get the same psi out. That means this is not an eigenvector of A. You will get an eigenvalue only if it is an eigenvector, correct? But this is not an eigenvector of A. So that you will not get any eigenvalue, correct? So normally what happens is if you operate A on psi, okay, it will become some other vector phi. This is the most general thing that will happen, right? So this is not an eigenvector. If it is not an eigenvector, it will change it. So a given state here is not an eigenstate of A. So that is one thing which we can immediately verify. That is, this psi is not an eigenstate state of A. That is something that we can verify. How to verify? You operate A on psi, you will not get psi out. Correct?
Yes, sir.
So then what else we should do? What can we do now to answer this question?
Then, sir, how can it give any measurement?
This is not an eigenstate of A, but A will have some eigenvalues, no? So when you measure A, you will get those eigenvalues as the result.
Yeah, if a measurement of A is made on a system in a given state.
Yes. So let us say for an argument's sake, okay, let A1, A2, A3 be eigenvalues of. We can find out what these eigenvalues are because matrix is given, right? So let us say these are eigenvalues of A. And then let us say some phi1, phi2, phi3 are corresponding eigenvectors. So if you are given a matrix, its eigenvalues and eigenvectors you can find out. Yes or no?
Yes, sir.
So let us say that we found out A1, A2, A3 are eigenvalues and phi1, phi2, phi3 are eigenvectors. That means A acting on this phi I is equal to AI phi I. I is equal to 1, 2, 3. Okay, so this is given a matrix, we can find these things out. Correct? Now, quantum mechanics tells us that if you measure A, okay, measure A in any state, result belongs to this set A1, A2, A3. Now, what changes from one state to other state is the probabilities will be different. probability of getting A1, probability of getting A2, probability of getting A3, that will be different for different states. But the result will not be anything different than this A1, A2, A3. Is this clear?
But sir, can we operate an operator on any wave function which is not its eigenfunction?
Okay, why should you operate the wave operator on the wave function?
To know the value of that observable.
So what do you do if it is not a wave, if it is not an eigenstate? To find out what is the value of that observable, you don't operate the wave function on operator on that one, but you take the expectation value, correct? So expectation value is simple only, right? Expectation value of A is you take psi A psi. For this psi don't have, you don't have to have it as an eigenstate, correct? This can be done with any state. Okay, so this is what we call as expectation value. But the given question is, if a measurement of A is made on a system in a given state, what is the given state? Given state is this state. What is the probability of the result is +1? So when they say result is +1, then we can conclude that one of the eigenvalues is +1, even without, because the result has to be always eigenvalues, no? So result is +1. Implies one of the eigenvalues of A is +1. Okay, you can find out eigenvalues of this one. Okay, but if you believe in quantum mechanics, you don't have to find out, because if the result is +1, then quantum mechanics tells you that the result has to be one of the eigenvalues, and if the result is +1, then it is definitely one of the eigenvalues. Is this point clear? This is an important point.
Yes, sir, this is clear.
Okay. Now, Deepika, is this point clear?
Yes, sir.
Okay. Now the important thing is that these phi1, phi2, phi3, which are eigenstates that I have said here, right? Corresponding to eigenvalues A1, A2, A3, they form a basis for the space. Okay. So this is the first concept. The second concept is that this phi1, phi2, phi3, these three states form an orthonormal basis of the state space. Eigenstates of any Hermitian operator, any observable, have this property. Now these are eigenstates of A. A is an observable, and hence they form an orthonormal basis. Okay, are you familiar with this? This forms an orthonormal basis for the state space.
Yes, sir.
Okay, now what can you do? If this is a basis, then you can think of expanding a given state in terms of this basis.
Yes.
So what do you get in that case? You will be able to write psi as some C1 times phi1 plus C2 times phi2 plus C3 times phi. Okay. Now, what are C1, C2, C3? They are related to what? Okay, let us say let A1 is equal to plus. One of the eigenvalues is plus 1, right? I will call that one as A1. Now, what is the probability of getting plus 1 as the answer? From this expression, can you read out what is the probability of getting A1?
Is it C1 square?
That is modulus C1 square. Correct? Now, how will I get C1? What is C1? How do I get C1? I know psi, I know phi1, phi2, phi3. How do I get C1?
Sir, get vector.
Go ahead.
Sir, we take a get vector. Means get phi and then psi vector.
Which phi? Phi1 or phi2 or phi3?
Yes, sir. C1. So that time we will get C1 phi 1. That means get vector and bra vector, sir.
This is bra. Okay. Bra phi1 get
Yes,
psi.
sir. Yes, sir. Sorry, sir.
Correct.
Yes, sir.
So this is how you get, right? So if you can find out C1, then you know what is the probability of plus 1. So to find out C1, what is that we should know? We know psi. We know psi that is given. And what we should find out to get C1? We need to find five. Okay. So that means what? You have to find out the eigenvector corresponding to the eigenvalue plus 1. Okay. So that is the only thing that I have to do. So 1, 1, 1, 1, 2, 1, 1, 1. So I have to find out 1, 1, 1, 1, 2, 1, 1, 1, 2 into some vector x, y, z is equal to plus 1 into x, y. I have to solve this one. That's all. Is that correct? So what I am doing, I am find eigenvector for eigenvalue plus 1. That is what I am doing here. So this will be like first equation is y plus z is equal to 0. Second equation is x plus y plus z is equal to 0. Third equation is also same, x plus y plus z is equal to 0. So these two equations are same. Okay. Okay. So now what is it that we are getting? We are getting y is equal to minus z from here. Okay. And if I put y is equal to minus z from these two equations, I will get x is equal to 0. Correct? So I have my xyz as 0 x 0 y minus y. And if I normalize this, I will get this as 1 by root 2 times 0 1 minus 1. This is the normalized. So what is my phi 1? I have found phi 1 to be 1 by root 2 0 1 minus 1. Is this clear, or are there some questions here?
Excuse me, sir.
Yeah.
Sir, please one more time explain the find eigenvector for the eigenvalue plus 1. The matrix 1, 1. That means that is a matrix A, sir.
Correct.
So the A operator is acting on X, Y, Z. That means acting on the state.
Yeah. So I have some eigenvector should be some 3-dimensional vector, right? I am calling that as xyz.
Yes, sir.
So this is basically A acting on some phi 1 is equal to phi 1 plus 1 phi 1. That is what this phi 1 is, a vector with 3 components. That 3 components I am calling it as xyz. Okay.
Yes, sir. Thank you. Yes,
now I have x plus y plus z is equal to x. So x will cancel on each side. I get y plus z is equal to 0. Correct? Here I get x plus 2y plus z, but already some y is there on the right hand side. So I get x plus y plus z, x plus y plus z is 0. From here, I get y plus z 0. Y plus z is 0. That means x has to be 0. So y is equal to minus z. So if I normalize the eigenvector will be 1 by root 2, 0, 1, minus 1. Okay.
yes, sir. I understood, sir.
Please note that I am not finding all eigenvalues and all eigenvectors, because I am using the given information in a very in a way that I do minimum work. I am not finding all eigenvalues and eigenvectors, because for this problem it is not necessary to find all eigenvalues, eigenvectors. So now what we will do, we have to find out C1. What is C1? C1 is given by this, right? Bra phi 1, ket psi. So what is our psi? Given psi is 1 by root 2, 0, 1 by root 2. Okay, so I will write this as, psi as 1 by root 2 into 1, 0, 1. Okay. So then what I will do here, I will have to find out. So this is your ket phi 1. What is bra phi 1? Bra phi 1 is 1 by root 2, 0, 1, minus 1. It's a transpose. It should be this one. So what is my C1? C1 is equal to bra phi 1 ket psi. So that is equal to 1 by root 2, 0, 1, minus 1. And ket psi is 1, 0, 1 into 1 by root 2. So this is equal to 1 by 2, 1 by root 2, 1 by root 2. And 0, 1, 1, 0 into 1 is 1 into 0. So you get only minus. So this is equal to minus half. So what is the answer? Probability to get plus 1 is equal to C1 square, which is equal to 1 by. This is the answer. Okay, any questions? Is it clear?
This is
Yes,
clear,
sir.
sir. Thank you, sir. But if we have some follow-up questions, like if we have degeneracy in the three-level system, then what will happen? Because two eigenvalues will be the same, probably.
Okay, so that means there may be another vector which has the same eigenvalue.
Yes,
Okay,
sir,
is that your question?
Yes, sir. But then confusion arises. How will we do? How will we do
Yeah.
that?
Yeah. Okay, I think it's a good question. So the question is, so what you are asking is that if +1 is degenerate, +1 is degenerate, then let us say you have phi1 and phi2, which are, that is a phi1 is equal to 1 phi1, and let's say there is another a phi2 is equal to +1 phi2. Let's say there are two states giving rise to same eigenvalue.
My guess, wild guess, is the addition of probability, because either the particle will be and phi1 or phi2. So or statement will be there. So addition of probability, not and statement, because it cannot be simultaneously at two of the levels.
Correct.
Levels.
Correct. They are mutually exclusive events. No, but yeah, that is fine. But what I'm thinking is that I told you that you don't have to find out all the eigenvalues and eigenvectors, but that is not the case if there is a degeneracy.
Yes, sir,
Because if you are not finding other eigenvectors, that means you are going to get less probability here.
Sir, can you explain it once more? Like, I missed your point. Like, if you don't get another eigenvalue, then?
No, suppose +1 is degenerate.
Yes, sir.
Okay, I have found one eigenvector here, right? I have found one eigenvector, but there may be another eigenvector which also gives the same eigenvalue.
Yes, yes.
Okay, in that case, I am missing that probability, right? I am only calculating one part of the probability.
Yes. We are assuming the a priori that it's a non-degenerate system.
Yes, yes. Yes, I'm just thinking, is there some clue in the matrix that it is non-degenerate? Okay, I think this matrix it is non-degenerate only. If you find the eigenvalues, you will know that it is non-degenerate.
We have to
But
find the eigenvalues, sir.
yeah, we have to find the eigenvalues to make sure that it is non-degenerate. Okay, but it's a good question. So let us think about it a little bit. So we will have to figure out how to do this degeneracy check without actually solving this one. But solving the eigenvalues is straightforward. But let me think if there is a way to do it just by looking at the matrix. Okay, any other question? This is a nice question. Any other question?
Excuse me, sir.
Yes, Deep.
Sir, this problem we will find the probability of positive one, sir. That means we will find the probability of positive one, sir. Why we will not get 1/4 like that, sir? That means always we will get a positive one. Why we should not take a probability 1/2, 1/4 like that, sir? That time how will find the 5/1? That means get vector 5/1, sir.
No, so what I'm saying is, if you understand this initial discussion, the result when you make a measurement of this operator A, the result will always be one of its eigenvalues. It cannot be anything other than that. So that is why I wrote here, no, result belongs to this set of eigenvalues always. Okay, if 1/2 or 1/4 is among the eigenvalues, then you can get the result. Otherwise, you cannot get such result. You follow, no? So they are saying the result is +1, means +1 is one of the eigenvalues. If they give the result is some -1, then -1 should also be in the eigenvalue. If you are saying you are measuring this, your meter is showing 1/4, then 1/4 has to be one of the eigenvalues. Now, if it is one of the eigenvalue, then corresponding eigenvector you can find out just like what we found out with +1, right? The same way you can find out the eigenvector for the other eigenvalue also.
Yes, sir, I understood, sir.
So what I suggest is, I mean, I don't want you to stop this problem with this thing. What I suggest is, you find out the eigenvalues of other eigenvalues of this matrix. Okay, so find out the eigenvalues of this matrix, and then you, just for practice, you find out what is the probability to get, if you make measurement of A, what is the probability to get other eigenvalues other than +1. Okay, so this is a 3×3 matrix, so its eigenvalues you can find out. One of the eigenvalues is +1. So you write down characteristic equation. Okay, it will be a cubic equation. Since you know one eigenvalue, no, you can get quadratic equation, because you divide that cubic equation by lambda -1, you will get other quadratic equation. You solve that quadratic equation, you can get two other eigenvalues. Now find out eigenvector corresponding to each one of that eigenvalue. That means instead of ket phi1, you find out ket phi2 and ket phi3. And then find out C2 and C3, mod C2 square and mod C3 square. And then show that all these three probabilities will add up to 1. They have to add up to 1. Okay, so this exercise, I think you can continue. Okay, it is doable, right?
Yes, sir.
Okay, so if you understand this, then you please continue this, then you will get a complete understanding of this.
Sure, sir.
Okay, so now let me go to the next problem.
Can I make a point here? Like,
yeah,
just
please.
for 1 minute. Like this problem captures the indeterminacy of quantum mechanics, I think. But if we have the psi equals to one of the basis vectors, then the problem will become determinate. No, sir.
That is initial, that given state is one of the eigenstates.
Yes, if psi is like phi1, get phi1, then the problem will become determinate. No, sir.
Yes, then the probability to get +1 becomes 1. And nothing else will be there.
Yes, sir. So can we introduce the concept of the entropy here? Because this is not so relevant, but I would like to raise this point because like we have the PMF, right? Probability mass function, not the probability density function, because we have only discrete values. So if we deterministic outcomes contain no information, we know that. If we know that the like both sides of the unbiased coin is heads, then if we toss the coin and measure the outcome, then we already know that the outcome will be head. So we don't find out any information. Sir, hello.
Yeah. Go ahead.
So like, but as we go to the non-basis states, so we get like a PMF. So with information content increases, and from information content we can use the average information content. So that will be the entropy, information theoretic entropy. Average information content will be the entropy, no sir. The amount of surprise, average amount of surprise. So like we have heard about different kinds of entropy, like Shannon entropy and von Neumann entropy, but that's like, but we use that very basic kind of entropy concept of basic entropy, because as I was thinking, we were solving this problem, this question is coming to my mind.
Okay, let me just make only one comment here, that most of these entropies that you are referring to, Shannon entropy or von Neumann entropy, all these entropies are associated with certain lack of information that is coming because of largely our ignorance.
Yes, sir.
Okay, the information loss is kind of man-made.
Yes.
But here, once you say that you have a quantum state, and which is a superposition of eigenstates here, and you don't know, this is somehow treated as an intrinsic indeterminism. This randomness is not out of any ignorance, because any ignorance that where we define those entropies, if you put in some effort, you can actually improve your knowledge. You can get more information. But here, it seems that this kind of a quantum superposition, there is no way that we can improve. So this is somehow, it is like a rock bottom. That means you cannot get any more information than this.
Okay, so thank you, sir. I'll think about it.
Yeah. Okay, so now let us look at this problem. Now I am considering two operators, okay, acting on the same three-dimensional kind of state space. In this case, both A and B are real. Now, if you look at A is, okay, I guess we don't even have, I don't know if it is a mistake. So let us keep this also at 0. So this is a diagonal matrix, right? A is diagonal. So that means A minus C. That means already it is diagonal. So we have eigenvalues. You can read out eigenvalues. So eigenvalues of A are A minus A minus. Two eigenvalues are same. That means what? Minus A is degenerate. Okay. Can someone tell me what are the eigenvectors corresponding to these eigenvalues?
So 1 0 0 0 1 0 0 0.
Ah, very good. So I have an eigenvector which is 1 0 0 0 1 0 0 0 1. But these two eigenvectors have got the same eigenvalue. Okay. Now, so the first thing is, obviously A exhibits a degenerate spectrum, and that is what we have seen, minus A minus A. Does B also exhibit a degenerate spectrum? How do you verify that? We have to find out the eigenvalues of this. Okay. Now, finding out the eigenvalues of this kind of a matrix is a little bit easy. like you see, this matrix can be seen as a block of 1 by 1 matrix, and here 0, here 0, and another block of 2 by 2 matrix. That means one of the eigenvalues B. Now, what are the other two eigenvalues? You have to find out. Other two eigenvalues you can find out by simply. So if you want to find out the eigenvalues of this matrix, then this is lambda square minus IB the whole square. That is minus I square minus IB the whole square is equal to 0. That is lambda square plus B square is equal to 0. Correct? I square is minus 1. So lambda is equal to plus minus I. So we have eigenvalues of B.
So one doubt, sir. Is
Yeah.
here now observable? Like it cannot be, right? Because it's not Hermitian.
Okay, so maybe we can simply remove this I here. I think I have directly taken this from book, but I think we can remove this I. If we remove this I, then this is minus B square. So minus B square, so plus minus I. So if you see, you have B, B minus B. So there is degeneracy here also, because you have B, B and minus B.
Sir,
Yeah.
what is wrong with that I?
No, if you have I, this is this Hermitian? That is what he is asking. So did you check if it is Hermitian? So B0, 0, you can take A and B are real. That's what you saying. So it is not Hermitian, because you will get minus IB and things like that, right?
Okay.
If one of them is minus, then it is fine. Okay. For example, you may have minus I here and plus I here, then that is a Hermitian. Okay, so let us remove I, doesn't matter. Okay. So if I don't have I, then you know this is B, B minus minus B. These are the eigenvalues. Now you can show that it will commute. Show that A and B commute. How do you show that? You can say, you can of course directly multiply and show that, but I want you to understand this. So if you look at this also in this block structure, so this is one block and this is one block. Okay. Now this block, if you look at this block is like minus A times 1001. Correct? Now you know identity matrix will commute with every matrix. That means if this block, whatever is this matrix, this block will always commute with this. That means what I'm trying to say here is, I'm trying to say that if you have a block matrix like this, there is a 1 by 1 block, and then you have a 2 by 2 block, which is identity into some constant, let's say some minus A in this case. This matrix will always commute with a matrix which has a 1 by 1 block here, and here you can have anything, let's say A0, A1. Okay, so here you can have any elements. So this commutator will always be equal to 0. Okay, so this you can verify. I can also understand, because this block identity will always commute with any other block. So I don't even have to verify. By looking at the block structure, I can say that these two commute. Okay, now the important question is this. This 1 0 0 0 1 0 0 0 1. Okay, so the show that AB commute is something which we can understand. So AB commute. Now we know the eigenvectors of A: 1 0 0 0 1 0 0 0 1. Now are they also eigenvectors of B?
Okay.
1 0 0, is it an eigenvector of B?
Yes.
Yes. What is the eigenvalue?
B.
B. 0 1 0, is it an eigenvector?
Yes. But it's also B, like eigenvalue.
Okay, let us look at like this. A on 1 0 0 is A 1 0. B on 1 0 0 is B 1 0 0. Now A on 0 1 0 is minus A 0 1 0. B on 0 1 0 is what? B on 0 1 0 is B times 0 0 1.
Sir,
Yes. Is this correct? B on 0 1 0 is B times 0 0 1. Is this
hello,
correct?
sir.
Yes, there's. Tell me this. Hello? Am I audible?
Yes, sir. Can you, sir, please repeat what you said in the last 1 minute? I was disconnected, so I don't know what you are writing.
So what I'm saying is that these eigenvectors of A, which are 1 0 0 0 1 0 0 0 1, I am asking, are they also eigenvectors of B? So I am examining that. If I take 1 0 0, A on 1 0 0 is A times 1 0 0. So this is an eigenvector of A. This is also an eigenvector of B. Whereas 0 1 0 is an eigenvector of A, but it is not an eigenvector of B, because when you operate B on 0 1 0, I will get B 0 0 1. The same vector is not coming out. You follow?
It's not a degeneracy because it's not a complete set. The degeneracy will not allow a complete set.
No. See, this is a complete set only. So this set is complete set, but it is not necessarily that all eigenstates of A have to be eigenstates of B also. Okay, so that is important to note. Similarly, when you write A 0 0 1, you will get minus A 0 0 1. Whereas when you take B 0 0 1, you will get B 0 1 0. So what is the conclusion? The conclusion is that these two eigenstates, so this 1 0 0 is common eigenstate of AI. Whereas other two, 0, 1, 0 and 0, 0, 1 are eigenstates of A, but not B. So this is what we have found. Now the question is, find new set of orthonormal vectors which are simultaneous eigenstates of both A and B. How do we find? Any idea? See, 0, 1, 0 and 0, 0, 1 are eigenstates of A with the same eigenvalue. Correct? The eigenvalue is minus A, eigenvalue is minus A. That means any linear combination of these two states will also have the same eigenvalue. It will also be eigenvector with the same eigenvalue. That means if I take alpha times 0, 1, 0 plus beta times 0, 0, 1. Okay, so divided by square root of mod alpha square plus beta square. Okay, if I take this, when I operate A on this, I will get minus A into this state. Is that clear? That is the advantage of having degeneracy. Because if A is linear operator, acting on this, you will get minus A out. Acting on this, you will get minus A out. You can pull out minus A, you will get this A. So that means, so what is this vector? This vector is for us 0, alpha, beta. Okay, I have to have two vectors, right? So 0, alpha, beta, 1 by square root of mod alpha square plus mod beta square. This is one vector. And other vector should be orthogonal to this. Okay. And so 1 by square root of mod alpha square plus mod beta square into 0 minus beta okay, alpha star beta beta alpha. Okay, alpha star beta star, something like that. If I put, when I take these two are orthogonal, because alpha star, beta star, alpha star, so that you cancel away. So these two are orthogonal, and then you can have this. So A operating on these two orthogonal vectors is also gives you minus A plus E. Now, what is the point? The point is that we have to find alpha beta such that these two vectors are eigenvectors of B. Already they are eigenvectors of A, but we should find alpha and beta such that they are also eigenvectors of. Okay, that is what is the situation here. Now, I can just give you the answer. You can say that alpha is equal to 1 and beta is equal to 1. Is the choice which will be an eigenvector of B and also eigenvector of A. That means these vectors are 1 over root 2 times 0, 1, 1 and 1 over root 2 times 0, 1 or 0 minus 1, 1. These two vectors are eigenvectors. So now if you take these three vectors, so including 1, 0, 0, 1, 0, 0 and this, these three vectors will form a complete set of eigenstates of both A and B. These are eigenvectors of both A and B. Okay. Now, how do you find them? You find, so if you look at that block diagonal form, so the block diagonal form of this matrix is given by 0, 0, B, B, 0, right? So the block form is, so this form, that is basically 0, B, B, 0. Okay, so now you find out eigenvectors of this matrix. This is basically B times your sigma x matrix, right? The Pauli matrix of sigma x. So sigma x is just 1, 1 and 1 minus 1, right? Or minus 1, 1. So that is what will be your y and z. Okay. So you have to only diagonalize a sub block matrix in this case. That will give you the other two vectors, which are common eigenvectors of A and B or simultaneous eigenvectors of both A and B. Okay. So any question here?
So this eigenvalues and eigenvectors which are common to both the operators, those are made possible only because they both had degeneration.
So the concept is something like that. If A has a degeneracy, then you are guaranteed that there exists another operator B which commutes with that. And if you have two operators commuting with each other, then you can find a complete set of common eigenstates to those two operators.
So can you repeat? I couldn't hear in between.
What I'm saying, if suppose you have an operator A and it has degeneracy, then you are guaranteed that there exists another operator B that commutes with A. And if you have two commuting operators, you can find a complete set of common eigenstates to both operators.
Okay.
Is that, yeah. Okay, so should we do our classes like this? I choose some problems and then clarify concepts or cover concepts through such problems. Do you think that this will work better than teaching concepts straight away? How do you think this works?
Yes, sir, it is more interesting than usual classes.
Okay, this is more interesting. Okay, but anyway, I think number of people are less, but I can only ask feedback from those who have attended. So Debanjan, you tell me, you are attending earlier classes also, and do you think we should do this? This is better?
Yes, because these are more insightful. This way of approaching the quantum mechanics, I find it more insightful than the regular classes. Like those are a bit cliched, like not your class, but like usual way of approaching quantum mechanics. Like people are doing it like for a long time like that. Yep.
Okay, so I think then we will continue like this for some classes and see. Deepika, you have any?
Sir, I get more information from this type of problem solving, sir. Previous classes, I have a more language problems, sir. So I could not easily understood what they said. So
Okay,
that's my
so
problem, sir.
here language is less, mostly mathematics. Okay, but
Sir,
anyway,
no, sir. This way
go.
I can easily understood, sir.
Okay, okay, very good. Pandya Rajan?
Sir, more interested, sir. I think I interested
Do you-
the problem.
Do you also have a language problem?
Yes, sir. Yeah.
Where are you from?
Madurai, sir.
Which college are you studying?
Yadava College, sir. MSc second year.
Okay. Deepika, you are from which college?
Sir, I'm from Pollachi, sir, Udumalpet, Government Arts College, sir.
Government Arts College. Okay.
Yes, sir.
Okay, so I think if this is working well, then we will continue like this for some more classes. Okay, so then we will stop here. Professor Yogarajan, can we stop?
Professor, if there are no more doubts for the students, I think stop.
Yeah.
So, shall I stop, Professor?
Yeah.
Okay, Professor.